Hi there, I'm Renee, and together with my project partner Joey, we made a constant current PID controller for our final project. This ended up being a much harder project than we originally thought when we first took it on, but we learned a lot along the way and ended up having pretty big success in the end. So what actually is that? Well, what it is it keeps a constant current across the load even if the resistance of the load or the supply voltage changes. It responds fast with tunable feedback depending on the application. And some of those applications could be motor control, lithium-ion charging, driving high-power LEDs, a lot of options. And we chose this project because we were interested in learning about op-amp integrators and analog control systems. So here's our design overview. Basically, we'll go into this more when we get into the simulation, but we take our desired current, the current that we want to set from the slide potentiometer, we compare it with the feedback from the current going through the shunt resistor with the difference amplifier, and then we feed that into our PID controller stage, which spits out the analog voltage that corresponds to the current we want to set, and that goes into this PWM converter that compares it against a triangle wave. And I'll hand it over to Joey to talk more about the simulation.
So the first part of our circuit is this current sensor, and the current sensor consists of an instrumentation amplifier and the high current path. The instrumentation amplifier has a gain of 100 and is measuring the voltage across the shunt resistor. Its inputs are DC coupled via RC low pass filter. The high current path has a load resistor, which right now is 4 ohms, and the shunt resistor, which is 0.1 ohms. It also has a low side MOSFET switching at various duty cycles to limit the current. So the way we design the circuit is that whatever current going through the load, the output of the instrumentation amplifier will be 10 times that, but in voltage. So for example, if the current going through the load was 0.2 amps, the output will be 2 volts. This is how we convert the current through the load into an analog voltage for the rest of our circuit to work with. So you might be wondering how we take a current sensor like this and turn it into a constant current device, meaning we can change the supply voltage or the load resistance and still get a constant current, assuming our supply voltage is capable of supplying the current demanded. Well, we're going to need an error amplifier. We're going to need something to tell us that, hey, the current you have right now is not right. And you can see here on one of the inputs, we're just going to have a potentiometer, which is essentially our reference voltage that we are setting for this. And what it's saying is, hey, I want the current to be this value. And that's going to be compared to what the current actually is, which is the output from this amplifier right up here. This error amplifier is always going to try to have 0 volt difference because we want 0 error, right? So you can see right now 2.09 and 2.07, there's almost 0 volts difference between the two, which means we are currently sitting in a good spot. And that's all due to the PID controller, which I'll go over next. But what's going to happen if I make a sudden change in the supply voltage? We can see how the error amplifier reacts. So if I increase the supply voltage, you can see here, all right, now there's a lot of error. The current that we are demanding is not anything close to what the current actually is. So what's going to happen is our PID controller is going to try to correct this and give us 0 volts again on the output of the error amplifier. And that's what you're seeing here. So it might take a second, it might oscillate around 0, but eventually it's going to stabilize to 0 volts over here. All right, so now the question is, what is a PID controller and how does it help us achieve 0 error on the error amplifier? Well, we're actually going to take our output V error and we're going to input it into these 3 stages: the proportional stage, the integral stage, and the derivative stage. And these are each going to contribute their own separate response to the summing stage, where we essentially sum it all up and give our total output called ISET. And we can change how much each one's contributing if we just change the value of these resistors here. So for the sake of demonstration, I'm going to go over each individual amplifier here, and I'm going to show on the screen what happens if we change the supply voltage suddenly, so you can see how the amplifier actually responds. So the first one is the proportional stage, and this is actually just a normal inverting amplifier. So what you're going to see is the proportional stage is going to provide an immediate proportional response to the error. So a large error is going to be a large output, and a small error is going to be a small output. It's essentially the immediate correction signal. The next one is the integral stage, which is just an integrator op-amp. This one is actually arguably going to be the most important because it's going to accumulate the error signal over time. So if there's any persistent steady state error, for example, if our current is actually 1% lower than what we want it to be, then the integrator is going to pick up on this and slowly increase its output until the error is forced to exactly 0. And it's really helpful for us because it's going to hold on to this analog voltage that's later going to be used for the PWM generator. And this analog voltage is really important for getting the exact duty cycle that we need. So unlike the other amplifiers, when they have 0 error, they're going to have 0 output. But in this case, when we have 0 error, we're actually going to contribute nothing to the integral. So it's just going to hold on to this voltage here. And then lastly, we have the derivative stage, which is essentially an op-amp and a differentiator configuration. So what it's going to do is if we provide a sudden change in the supply voltage, like so, it's going to look at the rate of the change of the error, and if the current is changing very rapidly, it's going to provide a counteracting signal to dampen the response. It prevents overshoots and oscillations, and it's going to help stabilize the system. So I really didn't talk about the values that each one of these stages have in the PID controller, and that's because it's really subjective to your personal application. On Renee and I's PCB, we have potentiometers for each one of these stages, so they can influence the output really depending on how much we need. And you can see a PID controller can actually provide a critically damped, underdamped, or overdamp response, very similar to an RLC circuit. And earlier I was demonstrating the underdamp case because I kind of feel like you can visually see the PID controller correcting better than any of the other cases. But if we were to tune the values a little better, then we can get it critically damped and the response would be almost immediate. So once we're done with all the stages of the PID controller, we get the analog voltage on the output of the summing stage. And in this case, it looks like it's 200 millivolts. So this 200 millivolts is going to be compared to a triangle wave. You may remember from Wallace class that class D amplifiers compare an analog voltage to a triangle wave to generate PWM. And that's exactly what we're doing here. And this PWM is used to drive the low side MOSFET on our load. So that effectively is what's actually varying the current to our load. So now you can kind of see how the feedback system works as a whole. An element of the circuit is changed, like a change in the load resistance or the supply voltage. Error is seen on the error amplifier, and the PID controller will respond to the error and adjust the duty cycle driving the load until the integrator finally finds the correct analog voltage to keep the error at 0. This creates our constant current. So this is a quick demonstration of the system in action. You can see I have 207.5 milliamps at the start. I'm going to change the load from 8 to 4 ohms. And you can see the total system response here. I have the entire outputs of the PID controller, as well as the error amplifier and the current through the shunt resistor. You can see that if I divide the load in half from 8 to 4, it's just going to decrease the duty cycle, and we're going to get right around the same current with an error of 1.2% after the system does its total response. And here I'm just showing that if we start at 208 milliamps and we want to change the value of the current to the load, we can just change the error reference voltage, and the current's going to change.
All right, so now that we've heard about how the simulation works, this here is our schematic. It's pretty similar overall to the simulation. We have some things we needed to modify to make it work in the real world. Some things like adding terminal potentiometers so that we can adjust and tune the PID parameters in order to tune it for different purposes. We have a gate driver that in theory is needed for fast switching due to the capacitance on the gate of MOSFET. And as well for high current loads, we need to have 3 parallel resistors that are 1206 package that are able to dissipate all the heat. All right, so here's some highlights of our PCB layout. Off to the left here, we have our slide potentiometer that sets the set point of our current. We have a signal flow going from the top right through our different stages all the way down to the MOSFET down here, and then completing the loop we measure across the shunt resistor, and that goes back into the current sense amplifier. Our traces for power are routed on the bottom, whereas our signals are routed on the top, and both of those are separated from our high current path that's off to the right here for reduced EMI leakage into the rest of the system. And we also added a lot of test points on here to help out with debugging. And with that, let's go and see the demo of the PCB. All right, so this is our PCB here. As you can see, Joey's adjusting the current, and you can see the light for the PWM get dimmer and brighter. That corresponds with the duty cycle of the PWM driving the current changing here. And as you can see, as he does that, the current increases from 0 all the way up to 500 milliamps. And the duty cycle is changing to make that happen. And the levels of the slide potentiometer correspond with that on the PCB. All right, so here we have our circuit, and we have 1 resistor connected for 24 ohms load resistance. We have 0.206 amps and 59% duty cycle. And so now Joey's gonna connect the other resistor to make it 12.5 ohms. And as you can see, the current stays the same and the duty cycle changes to compensate as he changes that resistance. And now he's gonna change the voltage. And as you can see, the current stayed the same. And then with the lower resistance, it still compensates. All right, so the results of this project, in order to make it work, we had to bypass the gate driver due to weird loading effects on the PWM output, meaning that we needed to use a lower switching frequency of 5 kilohertz to be able to drive the gate reliably, which increased noise in the system. After lots of tuning in the system and a PCB reorder, we were able to get the feedback working very nicely. It compensates for a change in supply voltage or load resistance, as you saw in the video, keeping the current within 0.2% of the original value based on our tests. This is a comparison of the different types of damping that can show up based on how you tune the PID controller. The blue line is just showing the response of the error amplifier to changing the load resistance. Some of the lessons we learned along the way are always check the little details one more time than you think you have to. We have a lot of little things that could have been fixed by just one more QA pass. We haven't learned about the math behind tuning PID controllers yet, so we only know how to tune by trial and error, but we still managed to do a lot with that. And one key help along the way is that integrators allow the circuit to hold whatever voltage keeps the error at 0, and so that cancels out any steady state error we might have. In conclusion, we took on a much harder project than we realized, and we learned a lot along the way. We had lots of failures, but in the end, we exceeded our expectations, and it ended up performing even better than the simulation, with 0.2% error instead of 1%. Shout out to my project partner Joey for all his help, and thank you for watching this presentation.